Here of electrolytic cells. Kind of some wrap up and then a couple new little odds and ends today. First of all, electrolytic cells, we've talked about how they're non-spontaneous reactions. They require the application of some amount of voltage. And one application is electrolysis. And we talk about here electrolysis of water, but electrolysis not only of water, but it might also be electrolysis of any other compound. We'll get to some more of those details later on. Now, water itself can be broken down into its elements using an electrolytic cell. Because pure water is a poor conductor of electricity, a non-reactive ionic compound is often added. So a common one would be sodium sulfate. This doesn't take part in the reaction, but it does speed up because it allows the solution to more easily conduct electricity. This reaction usually uses inert electrodes because they will not participate in the reaction. So, first little thing here is let's calculate the voltage required under standard conditions to separate water into its elements in an electrolytic cell, given that sodium sulfate is in solution to allow for easy conduction of electricity. So you want to look at your strongest reducing agent, strongest oxidizing agent to get you started. So just to do this properly, we have water, obviously, which can act as both a reducing agent and an oxidizing agent. We have sodium in its solution, so we'll have sodium plus ions, and we're going to have sulfate 2 minus ions. We've got inert electrodes, which don't matter. So we look and we find, and you'll want to take a look. At this point, you may want to listen for a minute or two more, watch for a couple more minutes, and then pause. Up to you what you do with this. So we've got sulfate. Now, without any H plus ions, that's not going to be helpful to us. If we look at sodium ions they're very weak, but I guess we can list them as an oxidizing agent. Water, as we've seen in the past, can act as both a reducing agent and an oxidizing agent, and in fact, what we are going to find out, it's both the strongest oxidizing and the strongest reducing agent. So what we want to do is we want to look at, now at this point I'm only asking you to calculate the voltage. Now we could write out the reactions. We find water as an oxidizing agent, water as a reducing agent. So water as a oxidizing agent, I'll write out the reactions. You wouldn't have to do the whole bit of work here, but we've got 2 H2Os plus 2 electrons. And that's going to give us H2 gas plus 2 OH minuses. Okay. We're also going to have at the other electrode H2O as a reducing agent. It's a pretty weak one, but two H2Os. That didn't work so well. There's a 2. H2Os are going to go to 2 electrons. And then I lost it on my table. And it's not 2, that's why wrong one. 4 electrons. Plus 4 H pluses. Plus O2 as a gas. So one electrode is going to bubble off H2 gas, the other is going to bubble off oxygen gas. If we were to balance it, we would see that we actually have two OHs, or well, once we'd balance the electrons, we would also be forming water as a product, so we'd have to do some canceling. We don't have to worry about that. What we do need to worry about is calculating the cell potential. And our E cell here, we want to take the cathode reaction minus the anode reaction. Cathode reaction is going to be negative 0.83. And we're going to subtract the anode reaction, which is going to be positive 1.23. So negative 0.83 minus 1.23. And we will end up with our E cell being 2.06. Sorry, negative 2.06. So to do this, it tells us we're going to require negative 2.06 volts. Okay. Now we can make this reaction proceed more easily if we use H2SO4 rather than Na2SO4. What this does is it changes things up. Now, when we're looking at the species we have present, we still have H2O plus, sorry, I don't need to write a plus, we're just listing them now. We have H2O. Now H2SO4 in solution is going to provide us with H plus ions and sulfate ions. It's going to also have, that's everything. So now we have to start looking here, and we're going to find out and here's where we have to look at this pretty carefully. In terms of our, well, H2O we know is an oxidizing agent and a reducing agent. H plus by itself can be an oxidizing agent. H plus plus SO4 2 minus, so these two together can be an oxidizing agent. Making sure I'm not missing one here. And what we find out, alright, what we find here is that our strongest reducing agent is our H2O still. But because we've added the H plus ions, what we have happening is that our strongest oxidizing agent changes. And so our strongest oxidizing agent will initially be this, okay? Now we can tweak the conditions, and this tweaking the conditions is beyond Chem 30. We can tweak the conditions because if this H2SO4 is our strongest oxidizing agent, we're not actually going to get hydrolysis of water. If we let the reaction proceed, though, for a little while, eventually what we find out, and you'll see you've got the reaction, and this is plus 0.17 volts. Sulfate plus 4H pluses gives us H2SO3 and water. We'll continue to generate H plus ions even after all of the sulfate is gone. And so although this initially together is our strongest oxidizing agent, eventually we use up all of the sulfate. That's all gone, and we're left with just H plus being our SOA. In either case, and we'll calculate just quickly a quick E cell cell potential for both of them, our cell potential gets substantially lowered. And so if it's initially using the H2SO4, we are going to have that positive 0.17 volts minus 1.23 volts. And so this is going to be equal to negative 1.06. And after the sulfate is all gone, our E cell changes once again. Where we just have the H plus ions present. It's going to change once again, and it's going to be 0.00 minus 1.23. That's easy math. And we're going to have is equal to negative 1.23 volts. And so what you can see here is it's definitely more voltage if you don't have the H pluses kicking around. If you can get the H pluses to be around, then what we end up with is a much a lower voltage, less energy input required. Okay. So electrolysis, breaking something down into its elements, that works. That's one of the ways of using electrolysis, or sorry, of using an electrolytic cell is for electrolysis. We could also look at something like turning liquid sodium chloride, so liquid table salt, molten table salt, which is going to be quite a high temperature, into sodium metal and chlorine gas. And actually Sir Humphrey Davy did this back in the 1800s, I believe 1896 or something like that. He did this with liquid table salt. And so he basically would take the solid, the sodium ions, they wouldn't be aqueous, sodium ions, turn them into sodium metal, and the chloride ions in the liquid chlorine turn them into chlorine gas. The metal would sink to the bottom, the chlorine gas bubbles off, they're separated, and away we go. Another common use of electrolytic cells is electroplating. We did briefly talk about this already. Generally with electroplating, we take an inexpensive metal like steel or copper and we coat it with a layer of a more expensive metal like silver or gold. Sometimes we also will take metals that have other desirable qualities, like they're good conductance or good strength or good corrosion resistance, and we might plate them onto other metals. So metals like platinum, rhodium, gold can be plated onto less expensive ones. If you look at high-end stereo components, a lot of the ends of those end up being made out of gold, or at least plated with gold, because it conducts just a little bit better. And for people who claim that they're, audio buffs, they're going to be able to, they say, have better sound quality that way. The metal or object to be coated is the cathode. This is important to remember of the electrolytic cell. Ions of the metal that will be deposited onto the cathode are present in the electrolyte. We supply the minimum voltage. It allows the reaction to proceed, and it causes the desired metal to be plated onto the cathode. Depending on how we set up the situation, a voltage greater than the minimum can allow the reaction to proceed more quickly. We don't generally want to be too much greater than the minimum, because then we can set up other competing reactions. So if you wanted to plate a copper object with silver, the cathode is the object to be coated. So the cathode would need to be that copper object. The anode generally is going to be an inert material. And that's just so that it doesn't compete or add other ions, right? I guess we could theoretically use a silver anode, but that's fairly expensive. So we use an inert material, and the electrolyte would be some soluble silver compound in order to provide silver plus ions. So we want to calculate the minimum voltage required to plate silver onto a copper electrode. So we're going to have two reactions happening. We need to have the reaction of Ag+, and usually we get Ag+ from silver nitrate. That's a common one. So we're going to have Ag+, we need to add one electron, and we're going to get solid silver. Okay. And we're going to plate the silver onto a copper electrode. Right, so this is going to be the one reaction that's happening. Now, you've already talked about how you could do stoichiometry with this. The other thing we're looking here is, okay, minimum voltage. To figure that out, we need to know the other half reaction. To do that, we need to figure out, okay, what's our strongest oxidizing agent, strongest reducing agent, all those kinds of fun things. So what do we have present here? Well, we're going to have Ag+ present. We're going to have solid copper present. We're going to have water present. It's important to remember that water is there. And we're going to have the other ion that goes with this. We usually assume that's going to be not something that reacts, but let's assume it's silver nitrate. So we'll add nitrate ion. And then again, we go through our lovely table. And so we have Ag+, and we find out that silver plus is a oxidizing agent. We find out that solid copper is a reducing agent. We find out that water can be both oxidizing agent or a reducing agent. And nitrate by itself, we find out, is neither. And so now we figure out, okay, which of these is our strongest oxidizing agent? Water is very weak, so Ag+ is our strongest. Okay. And now we have to be careful with this. Copper solid seems to be our strongest reducing agent. But let's just remember, let's make my computer work too. Come on, sorry. Remember our little acronym here, Leora Garoak. Loss of electrons is oxidization, reducing agent at the anode. Copper, we've been told, is the cathode. So although this is a lovely strong reducing agent, it can't be where the reducing agent reaction is, because copper, here it is our cathode. Okay, so gain of electrons is reduction. The oxidizing agent, that's at the cathode, good. That's what we want. We want this reaction at the cathode. This stuff this half reaction here, this is our cathode one. It's plating solid silver onto the cathode. It means our other reducing agent, other than the copper solid, this is what's reacting at the anode. So water, even though it's not the strongest reducing agent present, water is the only one that's present at the anode. And so we have to make sure we know that this is the reducing agent that is at the anode. And so we're going to, if we're looking here at this, we're using the silver half reaction, and then we're using the water as a reducing agent, that half reaction. Okay, so we're not going to use copper for our half reaction here. This is the only part here that could get to be a little bit confusing, but the only reason that it is a little bit confusing is we have to remember what electrode is that copper. And in this case, it turns out that the copper electrode is in fact the cathode, which means it is not going to be the reducing agent, because the reducing agent, you're a reducing agent at the anode. Alright, so once we start writing this, we have the reaction that I've written at the top already here, the cathode one, and then our anode reaction is going to be the plus 1.23 volts that we were just dealing with. And so where we have two H2Os, giving us 4 electrons, I think, if I'm the right line, plus 4 hydrogen ions. O2 gas. Okay. So again, I'm not asking you at this point, you could come up with the overall reaction. I'm not asking for that. What I am asking you to do is to calculate the cell potential. And so we figure that out. It's going to be, we look at our silver, that's our cathode reaction. Is positive 0.80 minus positive 1.23 for the water reaction, and we end up with negative 0.43 volts. Now, remember that if more than one non-spontaneous reaction is possible, then the reaction requiring the least amount of voltage will proceed for as long as the reactants are present. And this is why electrolysis reactions can sometimes get to be complicated. We can think, oh, I want to do this reaction, but there's something present there with it that makes it so a different reaction occurs. So it's always things that you just have to be careful of. You have to make sure that you look at water if the electrolyte is present in an aqueous solution. Water has to be considered when determining the strongest oxidizing agent and the strongest reducing agent. Electrorefining is another process, and it's actually quite similar to what we were just talking about, except here, instead of an inert electrode, we use an impure metal as the anode. Now, several of the metals present at the anode are oxidized, but we take the desired metal and it can be preferentially reduced at the cathode, and that allows it to be recovered. The remaining undesirable metals form a sludge called anode mud, which drops to the bottom of the cell and they can be disposed of. Or, if we're wanting to get gold and it's a mixture of like gold, silver, copper, and other useful metals, we can then take that anode mud and further do electrorefining with it. A similar method called electrowinning involves recovering a desired metal from a molten or aqueous electrolyte through electrolysis. So you can make, in the case of electrorefining or electrowinning, let's say we're wanting to get silver and we want very pure silver, we would use a small amount of pure silver as our starter for the anode, for the cathode, I apologize. Small amount of pure silver as our cathode, and then what we do is we just plate more and more layers of silver onto it, and we get a very pure sample of silver. Same thing for electrowinning. Finally, we come to this bit here, the chloride anomaly. Now, we can normally or generally predict reactions by finding the strongest oxidizing agent, strongest reducing agent on the in a redox table. We add the half reactions, we determine the cell potential to predict either spontaneity or the required voltage. Sometimes this rule doesn't work, and there are exceptions. One that you need to know is called the chloride anomaly. So, if we did that very first, this is going all the way back to the very beginning here. Electrolysis, right? We looked at this. Now, I gave you sodium sulfate rather than sodium chloride. That was on purpose, because sodium chloride is an anomaly. In the case of producing oxygen gas and hydrogen gas in an electrolytic cell with aqueous sodium chloride, we look and we say, okay, so we have water, we have Na+, and we have Cl-. if we look here, Cl minus is right up near the very top on the right hand side, and when Cl minus and H2O are together, they make a very weak reducing agent. Sodium plus is a very, very weak oxidizing agent. Water by itself can be both a reducing agent and an oxidizing agent. What we predict we should get, is a number exactly like we had up here at the very beginning. We predict that water is going to be both our strongest oxidizing agent, strongest reducing agent. We figure that the cell potential should be negative 2.06 volts. Okay, so that would be our calculation. You just saw it on the video there. Now when we look at this, and this is one that you calculate the voltage required to produce hydrogen gas and chlorine gas in an electrolytic cell. Now this, because it's telling you it's going to produce hydrogen gas and chlorine gas, here we are going to assume that even though water is a stronger reducing agent than this water and the chloride together, we're going to, in this case, calculate as if water and Cl minus are the strongest reducing agent. So water is going to be our oxidizing agent, and so we look at that, and okay, that's our cathode reaction. So the E cell here is going to equal negative 0.83 volts, and we're going to subtract and go all the way to 5th from the top, minus positive 1.39 volts. And our cell potential here then is going to turn out to be negative 0.83 minus 1.39, and it suggests it should be negative 2.22 volts. This one here, again, we came up with negative 2.06 volts. The funny thing is, it tells us that this reaction should happen first. What actually happens is we produce chlorine gas. In the above situation, according to our rules, chlorine should not be formed, but it is. Now, the explanation for this is beyond Chem 30. That said, it has to do with the fact that oxygen gas should be produced, but for whatever reason, it requires extra energy before it forms. Chlorine gas should not be produced, but does not require as much energy as oxygen in order to form. And the reason, one of the reasons that the table can't accurately predict these few reactions is that it doesn't always take into account the energy required to form a specific gas in a specific reaction. Because all of these reactions are formed, these half reactions are calculated using H plus ions as 0, so as the two H pluses plus 2 electrons giving us hydrogen gas, that's 0. We have the table that we do have. There's a few places where we have specific reactions that we can't predict using the table. So the table's not perfect. That's basically the gist of this. The one that you need to know, even though there are other exceptions, the only specific one you need to know about is this reaction. And the reaction is that if you are using sodium chloride as your electrolyte, you will not produce oxygen gas and hydrogen gas. You will produce hydrogen gas and you will produce chlorine gas. Right, so for the weekend, you have, I gave you, it's called quiz number 2. It's mostly review of some of the stuff from earlier on in the unit. If you can have that done for Monday, we'll go through it together on Monday. Also, if you would be able to do your best to finish up with the unit assignment. Thank you very much.